Okay, looks like we've got everyone in. So officially, good mid-afternoon, everyone, and welcome to the Mid-Afternoon Masterclass as part of the University of Melbourne Science Festival and as part of National Science Week. My name is Julia and I will be your host today. Before I begin, I want to acknowledge the traditional custodians of the lands on which we're all zooming in from. I'm on Wurundjeri land today, which is also lands of where a lot of the work of the university is undertaken. I want to pay my respects to elders past, present and emerging, and extend that respect to all Indigenous people in the audience. And really importantly, at this time of National Science Week, I also want to acknowledge and respect that Aboriginal and Torres Strait Islander people have been researching and learning and caring for this land for tens of thousands of years. And so they are our first scientists. So, Mid-Afternoon Masterclass, this is a series of events happening at 2 p.m. All week, and we are hearing directly from Melbourne Uni academics working on interesting topics from a variety of different disciplines. Each session is just a quick 45 minutes and includes a presentation as well as time for Q&A at the end. And today, as we all know, it is lighting the dark universe. So it's all about dark matter. And I don't know about you, but I'd love to learn so much more than I already do. So we've got two wonderful experts here to explain it all to us. What is it and why are we going 1,000 metres underground to detect this dark matter? So without further ado, I want to introduce our two guests so they're not just sitting here on the screen without anything to do. So Bill Dix Melvin and Madeline Zarowski, thank you both for joining us today. How are you?
You're doing well, Julia. Thanks.
That's good. Thanks, Maddie.
Very good. Thank you.
That's good. Awesome. So thank you both. Now, I do want to introduce you a little bit more. And at this time, if I had two guests, I would usually say that I would do separate bios. But if I did do that, I'd basically be repeating myself. So these, my two wonderful guests have had reasonably similar, background and career up until now. So I will go through it reasonably similar. So both Bill and Maddie, they're third year PhD students here at the University of Melbourne. They both completed their Masters and Bachelors of Science also at the university, and they work in the field of experimental particle physics. And they're working specifically with the SABRE collaboration. Now, Bill specifically is working, has a focus on the detector calibration, reconstruction and modelling. And Maddie is modelling how different types of dark matter might interact with the detector. So I'm told that Bill is more hardware stuff and Maddie is more simulation stuff. And that seems like a nice overview, and I'm sure you're both going to go into it a lot more detail than that. But welcome, and thank you so much for both of you being with us today. Before I do, go on, I'd love to hear a little bit more from both of you before we hear about specifically about this area. But what is it about particle physics that really interests you so much? Maddie, I might just start with you. What is it about this area, and why did you decide to study it and do your PhD in it?
I have known I wanted to do physics since I was in about year 8 or 9, I think. I've always really enjoyed science, and I like the idea of just being able to, in a perfect world with infinite time, I would love to just sit and learn everything. But of course, that's not really possible. So I figured the best thing to do, if you can't do that, is to work out what the most fundamental things are. And, particles, the building blocks for everything else in the universe. So start from the bottom and work my way up.
Absolutely. That's a great reason to do it. By understanding particle physics, then I guess you've got the foundation for so many other things as well. And over to you, Bill. What is it? What is it about particle physics?
I guess I'd love to have this nice answer that was like, oh, it's what I always wanted to do.
Yeah.
I kind of ended up here because at every step, this was the most interesting thing. So I came to Melbourne University wanting to be an engineer, and I just had to take some physics classes. And kind of it's a snowballed from there that physics was always more interesting. And eventually I've ended up here. And I guess what really interests me about dark matter is it's such an unknown that we have these ways to try and measure it, but it really feels like you're kind of on the edge of what we know and what we don't. And I think that's a really interesting place to be.
That's amazing. And I mean, I think it's a great message to everyone out there about just continuing and studying the things that they like. And that's fantastic that you found that, and such a great thing that you had to do these subjects foundational to get into engineering, because who knows where your future would have been without it. So that's great to hear.
Absolutely.
God.
Sliding doors. Okay, So thank you so much to both of you. So out to the audience, just quickly, I'll just do a bit of housekeeping before we pass over to the presentations. So obviously we're on Zoom, it's a webinar, and neither myself, Maddie or Bill can actually see or hear you, but we'd still love to interact and hear from you. And there are two ways that we can do that. The first is if you look at the bottom bar of the Zoom, there is there's a chat function. So if you click on that, you'll be able to add comments as Maddie and Bill do their presentations. Also, highly recommend towards the end of the presentation, if you liked it, let them know, maybe with a well done, maybe with a congratulations, or my favorite, just simply say clap, 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 because that's what we would have loved to have heard or seen you do if we were all in the same lecture theatre normally. So that's the chat function. I'd love us all to have a bit of a quick taster of it, or a bit of a test of it, to do the test, but also for us to find out where you're all from. So if everyone in the audience can just click on the chat function, open it up, make sure you click everyone, make sure you're sort of sending that message to everyone, and just write in the chat where you are right now. So maybe it's the suburb you're from, maybe it's the school that you're zooming in from, maybe it's the state, maybe it's the country. We've had lots of different people from different countries. Oh, there's India as well, Doncaster, Melbourne, Beijing, Ringwood North, Kew East, Brunswick, Mortlake. Wonderful, we visited Mortlake a couple of years ago. Point Cook, so many different places. This is wonderful. Dubai, fantastic. Fitzroy North, Richmond, Kensington, and so many different responses. Fantastic. Max, 10 years old, Max. Welcome, Max. Fantastic. All right, amazing. Thank you so much for everyone. It's really great to see where everyone's from, and welcome to you all. Second thing I want to let you know is the down below there's also a Q&A function. So if there's any specific questions, please feel free to put their questions in there. Maddie and Bill will be doing separate presentations. So if there's any of them specifically for each presentation, we'll stop sort of halfway through, but otherwise we'll have a chunk of time at the end to try and answer as many as possible. So please put all your questions in there. We'd love to, I guess, answer those to ensure that this session is answering all your questions and having a nice overview for the audience. So then that's it. That's it from me. I'm going to pass over to our guests, and we can hear so much more about what we're all here to talk about, and that is dark matter. So Maddie, over to you. Thank you so much, and looking forward to hearing all about it.
All right. Thanks, Julia. Just as Julia did, I'd like to begin by acknowledging that I'm coming to you from the lands that belong to the Wurundjeri people, who also own the lands that UNI Melb is on. As well as that, I'd like to pay my respects to the Wotjobaluk, Jadwa, Jadawajali, Wagaya, and Jupagalk nations, who are the traditional owners of the Stawell region where our lab is located. I pay my respects to their elders, past, present, and acknowledge that all the other Aboriginal and Torres Strait Islander people who may be joining us today. I also acknowledge that sovereignty was never ceded. So today we're talking to you about dark matter and how Bill and I are hoping to, bring some light to this unfortunately dark universe that we find ourselves in. So the first stop on this journey, as it so often is why we think we're looking for this dark matter and kind of the evidence that it's there in the universe. Basically, there's a whole bunch of different ways that physicists have been able to probe the universe for the last decades or so. Things like looking at how galaxies collide, how fast they're moving, where the structure is in the galaxies and in the universe, how gravity and light interact with each other. And when we put all of these pieces together, it still seems like there's something missing. Basically, all of this evidence points to the fact that there's some kind of matter that doesn't interact with light at all. It doesn't interact in the way that any kind of regular matter that we've seen before. If you look at this plot on the right-hand side, all of the physics that we know and understand only actually makes up about 5% of the total universe. A quarter of it is made up of dark matter, which is what we're going to be talking about it. And then the 70% is called dark energy, which is basically just a fancy way of saying that we have literally no idea what it is. So we know that there's something out there, but how do we narrow it down even more? How do we work out what this something actually is? There's 3 different ways that we can try and detect dark matter. They're all kind of summarized by this arrowy diagram right in the middle, but I'll also go through them separately. So the first is collision, where you have 2 regular matter particles that come in, collide with each other, annihilate, and produce a whole bunch of different things. There's experiments that are already studying these kinds of processes, like the Large Hadron Collider in Europe, which is shown on the left-hand side there. One of the side effects of these processes is that you can create dark matter. And because dark matter doesn't interact with anything, it will basically look like missing energy within the detector. And we can infer its existence from that. The second way we can look for dark matter is by basically looking for the inverse of this effect. You can have two dark matter particles that annihilate each other and create normal matter seemingly out of nowhere. We look for this with these large telescopes, like on the bottom right-hand side of this slide, which point towards the center of the galaxy and basically are trying to spot this matter that pops into existence from out of nowhere. Finally, the process that Bill and I are going to be focusing on today is scattering, which is also known as direct detection, because in this case, you're looking at dark matter's direct effect on regular matter. You have a dark matter particle coming in, hitting normal matter, and then continuing on its merry way. Unlike collision and annihilation processes, these experiments are often quite a lot smaller. You can see in this picture up here that this one's about the size of a couple of people. All right, so what actually is direct detection, and how can you try and visualize something that doesn't interact with anything that we know? The way I like to talk about it is by imagining that you're trying to detect an invisible ping pong ball. So you've got our target just here, where our ping pong ball is coming in, hitting it, and then we can see the recoil of this target, even if we can't see the ping pong ball itself. On the right-hand side of this slide is a picture of our detector, which I'll go through in a little bit more detail later on in the talk, where the target, where we're actually hoping to see this interaction, is right in the middle here in those copper-looking enclosures. So why do we actually care about looking for this kind of scattering? What is it actually going to tell us about this pretend particle? Basically, by looking at these detectors over a long period of time, we're just trying to count the number of times that we see some kind of interaction that could be between dark matter and regular matter. I promise this is the only maths in my talk, and it's not even really that important. So what this expression is actually telling us is that the number of interactions that we see, R, is just given by the number of targets that we have, the properties of our projectile. So in this case, this weird looking symbol at the top here is called the cross section, and the bottom is the mass. And then the density and the speed of our projectile. So in this case, it's our dark matter, which is basically just telling us how fast it's moving and how many are moving towards us. If we want to think about this in our ping pong terms, we can replace that with a bunch of, targets out in the field, different ping pong ball properties, such as, ping pong ball color, what brand it is, something like that. And then our sort of tennis ball, ping pong ball lobbing machine that's just going to be hurling these ping pong balls at the target. Now, you probably could have told me that this was how you work out how many interactions there are without any of that maths behind it, but nevertheless. So because we're trying to observe these interactions, we want to kind of make them as easy to see as possible. So one big question that we've been trying to answer is, how do we design a detector that gives us the best chances of seeing something? We want to basically target the most likely properties that we think dark matter is going to have. We want to pick out a mass and a cross-section for dark matter that is going to be easy to observe with our detector. Of course, I haven't really explained to you guys what cross-section is. The official definition is that it's the measurement of interaction likelihood, which basically just means it's a measure of how easy it is to hit a target. That's why it's got the name cross-section, because it corresponds to how physically big a target might be. But in physics, nothing's simple. So there's a whole bunch of other things like magnetic charge, electric charge, how see-through something is, that's going to influence how easy it might be to actually hit a target. So when we're designing a detector, we want to pick our target that is going to give us a high probability of hitting, a high probability that dark matter is going to hit it for a particular dark matter model. So our target is an atomic nucleus. What we're looking for is dark matter. We put it into our love calculator. And we remember that, for those of you who haven't taken chemistry or physics in a while, an atomic nucleus is made up of 3 different particles. So there's a whole bunch of different types of dark matter models that people have described that mean that, maybe dark matter only likes interacting with neutrons. Maybe it only likes interacting with protons. Maybe it only likes electrons. So you basically first have to pick a dark matter model that you think is likely, and then pick a target that's going to let you observe that. So for example, if we think that dark matter only interacts with neutrons, we'll pick some kind of element as our target that has a very neutron-heavy nucleus to kind of up our chances of an interaction occurring. The second thing that we have control over is the mass of our target. What's important isn't necessarily just the mass by itself, but how heavy this target is going to be relative to our dark matter. If we're imagining throwing our invisible ping pong ball at either a bowling ball or a beach ball, Both of these have a similar size, so they've got the same physical cross-section. But if I throw my ping pong ball at the beach ball, that's going to go flying, whereas the bowling ball is going to stay stationary. So if I can only see what my target is, I'm obviously going to want to pick the beach ball because I can actually see when something's happened. So we want to pick a target that has a similar mass to what we think dark matter has in order for the recoil energy of the target to be as obvious as possible. All right, so I've talked you through a little bit about how we calculate what the interaction rate is. When I plug all of those into my fancy models, I end up with the simplest answer possible, 1. For dark matter, we expect around 1 count per day per kilogram of target material that we have. Unfortunately, this turns into a bit of a needle in a haystack type search because on the surface of the Earth, there's over 1 million counts per day per kilogram of target material of just background trash, things like particles being produced in the upper atmosphere, radioactivity from different sources, be it, actual uranium in the Earth or human bodies. But luckily for us, dark matter has a very special feature, and that's the fact that even though this rate of interaction is expected to be quite low, it modulates. So what that means is basically, as the sun at the bottom of the screen here is moving through the solar system, it's actually moving through a wind of dark matter. In this picture, it's called WIMPs because that's just a specific model. It doesn't really matter too much what it is. But it's moving through this wind of dark matter. And so as the Earth rotates around the sun, for about half of the year, it's moving in the same direction as this wind. And in the other half, it's moving in the opposite direction. This has the same kind of effect of if you're walking through the rain on a really windy day. If you're walking into the wind, it's going to feel like there's a lot more rain hitting you than if you're walking with the wind. Exactly the same thing happens here, and it turns out that in December, regardless of where you are on the Earth, you expect to see fewer dark matter interactions than you do in June. Another way of looking at this is if we have a look at this animation here. So we've got the sun in gold just there and the Earth moving around it. And you can see that the interaction rate we expect to see looks like a sine wave. So we've got that kind of modulating feature, which is really obvious. And this is basically considered a smoking gun for dark matter detection. The great news is Bill and I can pack up our search because somebody else has already seen this. An experiment called Dama Libra uses a detector that has a sodium iodide target, which is basically very similar to just your regular table salt, where they put these crystals inside a copper enclosure and then inside a whole bunch of shielding to make sure just the dark matter is getting into the crystals themselves. And these guys have been observing a signal that looks a lot like dark matter for the last 20 years or so. You can see some of their data in the bottom of the screen here, where the points are from the experiment itself, and the line is just that projection of exactly what was on the last slide there. So this fits dark matter suspected modulation very, very well, and everything's great. We've seen it, we can pack it all up. Unfortunately, nobody else has seen this kind of interaction. So as I said before, the two things we care about for dark matter are its cross-section and its mass. So this kind of plot is how we typically demonstrate how good an experiment is at probing different types of dark matter, where each experiment gets a line, and then anything above that line is a dark matter mass and cross-section that experiment should have been able to see an interaction for. So for NEWS-G, for example, anything up here should have been observed at this experiment. So if they don't see anything, that parameter space is ruled out. So you can see that every single one of these experiments on this plot, pretty much, are ruling out what Dama says that they've seen. So these two dots here are dark matter models that fit what Dama's observed. So this is pretty disappointing, to be honest with you, the fact that Dama's seen something that looks so compelling and everybody else is like, nah, you're wrong. But there is, however, one final bit of hope here, one last caveat. And that's that everybody else on this plot is actually using a different kind of target. So basically any experiment with the letter X in it is using a target called xenon. Other people use something called germanium and stuff like that. So it could be that dark matter just has some really finicky, specific model that only likes interacting with sodium iodide. And so in reality, nobody else is going to be able to see what Dama's seen except for Dama. So that's where our experiment SABRE comes in. Bill likes to call it the most boring place in the world because we've put so much effort into designing this experiment to make sure that nothing but dark matter gets into this detector without us knowing about it. So essentially what we have here is our sodium iodide target in the center here. Because we're using exactly the same target as Dama is, we should be sensitive to exactly the same signal they've seen. If Dharma has seen dark matter, Sabre will be able to too. No ifs, ands, or buts about it. This target is then placed within what we call a Vito vessel that's filled with something called a liquid scintillator. Ours is basically the same chemical composition as your everyday dish soap. So I like to say this is just salt and dish soap underwater for a very long time. And this dish soap is going to light up when particles pass through it. So it gives us a way of identifying any background processes that could be pretending to be dark matter and rejecting them from our data set. This is then placed inside a whole bunch of shielding to reduce external radiation. And then we've got muon detectors on the top. Muons are an external background that comes from the atmosphere that do have a modulating signature that's similar to that of dark matter. So it's very important that we identify that so we can remove it. So when we put all of this stuff together, we basically have that the components on the left are there to reduce the internal backgrounds of the experiment. This guy needs to be super, super pure in order to observe that 1 count per day per kilogram rate that I talked about. So for example, our crystals are so pure that the human body has 200,000 times more potassium than the crystals do. 200,000 times more radioactive. You don't normally think of human beings as being radioactive, but we're too radioactive to go and stand next to this experiment for long periods of time. Through a lot of very, very hard work, we've managed to get down to a background rate that's about 0.36 counts per day per kilogram, which is very impressive and would make us one of the lowest background sodium iodide experiments in the world. The components on the right-hand side, as I said before, are there to reduce the external backgrounds. So you can see that plot at the bottom, which is giving you what the muon rate is going to be, is modulating in a similar way to what the dark matter is. So with a much, much higher rate. So we need to be able to observe that to get rid of it. When we put all of this together, what we actually hope to see is something that's totally free of background and free of muons, which is what this plot is now. This is something that I simulated earlier in the year, and it's what exactly the interaction rate that we should be seeing if Dharma is right. We should see just under 6,000 counts a month that can be attributed to a dark matter interaction. As well as that simulation, I do get to do some hands-on work every now and again. I've worked quite a lot on actually reducing the background within our crystals. So on the right-hand side here, you can see exactly what one of our crystals looks like that's going to be going down into the mine next year. What's noticeable about this is it's actually one single individual crystal. So if you look at, table salt, or you can see those big flakes of like Murray-Darling salt you can sometimes get, those guys are actually made up of a whole bunch of little small kind of individual lattices that are connected together. But ours is whole and perfect, and you can see straight through it with no kinds of weird optical effects happening, which is very, very important for what we're trying to do. On the left-hand side there, you can see me working through one of the purification tanks we've got, which we use to try and help reduce exactly that potassium that I was talking about. And in the middle, there's me excitedly holding one of the crystals with 3 pairs of gloves on. That's right, 3. You have to go through an air shower, put a little Charlie and the Chocolate Factory suit on, and then put 3 pairs of gloves on if you want to touch any of these crystals. All right, so hopefully I've covered for you guys what the dark matter interaction is and how frequently we think it's going to occur at our detector. So now I'm going to let Bill take over, unless people have any questions, to talk about how we're actually going to detect it.
That's amazing. Thank you so much, Maddie. We did have a few questions come through that seem quite specific to your presentation, so we can just maybe answer those quickly before heading over to Bill.
Yep.
There's a couple just about the Dharma detector specifically. So why is there copper at the center? This is from Ethan. Why is there copper at the center of the Dharma detector? Why not another metal?
Copper is something that's quite easy to make low radioactive, and it's also nice and reflective. So it's the metal of choice for all of our experiments. You can see that ours are also copper, and so are the little tubes that suspend the crystals within our vessel.
Mm-hmm. Okay, amazing. And also with the Dharma results, so from Jane, are people proposing any different explanations of the Dharma results other than dark matter?
That probably depends on who you ask. It's kind of it's something that's a bit annoying to me, is everybody is very quick to say, oh, it's not dark matter, it's not dark matter. But nobody's really providing a compelling explanation for what it could be. One of my favorites, though, is that somebody suggested that their PMTs, which Bill's going to explain to you in a minute what those are, but basically they're used to actually, you attach them to each end of the crystal and they detect the signals themselves. They suggested that those have a helium leak, and as the temperature changes, the amount of helium changes. So you might get a weird modulating effect like that. But people do have to do quite a lot of weird gymnastics to try and explain this without using dark matter, which is why, I don't know, even though it's quite constrained, in my heart of hearts, I do hope it's dark matter.
Fair enough. Final question from Luna. So thank you for asking that question, Jane. And also we've got a thank you from Ethan in the chat as well, just for that first question. And from Luna, how did you guys reduce background radiation count?
So there's a whole bunch of different ways of doing that. One of them is in this picture just here. So as you might have guessed from what I was saying, one of the biggest problems is potassium, both because if you look at the plot at the bottom here, you can't really see it very well, but the double peak at around between 2 and 4 keV, that's from the potassium. And if anybody remembers their periodic table, potassium's right underneath sodium. So they're actually very, very similar chemically. So you have to do a whole lot of very careful filtering, essentially, of the powder that we get to grow the crystals in order to get rid of any potassium that's left in there. There's also a whole bunch of other things we have to do about like carefully drying the powder to make sure there's no water that can interact with it because it dissolves really easily. There's a whole lot of different ways of purifying it, and I won't give all our secrets away just yet.
Fair enough. Keep us guessing. Okay, awesome. Well, thank you so much. Just a few questions there, just to catch everyone up, and then so over to you, Bill. So if you just stop sharing Maddie, thank you so much. And I believe we've got a bit of a lab tour coming up, Bill.
Yeah,
I'm very excited about.
I'm actually just going to, before I start showing my slides, I'm going to show off. Maddie had a picture of the Sabre enclosure, and it had these giant copper tubes in it. So I am fortunately actually in at the lab today, so I can show off some of the things. I'll admit it's not polished and shiny, but this is one of the copper tubes that will house part of the Sabre experiment. And there's a few different parts of the experiment behind me, which I'll go through in various places, but I just wanted to show that and avoid dropping it on anything nice over here. So Maddie has talked about what an interaction is, how frequently it might occur, and what affects that. I'm going to try and talk you through how we detect it. So if you've got any questions about detectors, hopefully I can at least have a go at answering some of them now. So the first question is, what do we actually see when we've got a detector? So we already know that we have our dark matter particle. It comes in and interacts with the nucleus, and it scatters off. And when it does that, it gives our nucleus over here just a little bit of energy. But I guess the question is, how much energy does it have? So you heard Maddie say before 6 keV. So that's one of the units we use for energy. And we use units like this in particle physics because we're talking about a really small number. So this 6 keV, and I'm sorry, there's a few big numbers here, is 1 times 10 to the minus 15 joules. So to try and put some context, because that's a very small number, that's 0.00015 zeros and then a 1. So that energy, you'd need 1 trillion of these collisions to get the exact same amount of energy as it takes to lift a pencil 1 centimeter in the air, right? That's not a very hard thing to do. And you need so many of these events to happen. So how can we even try and see these collisions if they're so small and there's such a small amount of energy? And the answer is we use these special targets. So we don't just use sodium iodide because it's boring and because not a lot's happening. We use it because it's a scintillator. So a scintillator is a target that turns collisions into light. I have here a giant lump of plastic scintillator. The reason I can't show you one of our crystals is, aside from being really precious and really pure, they also just dissolve because of the water in the air. So I have only these things to show you. So we have materials like this that when they have particle interactions will end up giving off light. I guess the question now is, how do we see this light? Because how much light do these collisions produce? Well, because there's only a little bit of energy, they only make a little bit of light. So about 30 photons on average. So you might have heard of the photon. It's our fundamental particle for light. It's the smallest amount of light you can have. So again, to try and put that number in some context, a normal light bulb that you have in your house makes 10 quintillion times as much. So that is 10 followed by 15 zeros, as much light in 1 second. Or another way to think of a number that big is there's roughly 10 quintillion grains of sand on the Earth. So we're trying to detect 30 grains of sand effectively out of all of the sand on Earth in each pulse. So to measure this, we have to use these really sensitive light detectors called photomultiplier tubes. So you can see here, there's a picture of them there. I have a few of them sitting behind me that we're actually going to use for the SABRE experiment. So the big one that you can see the photo of here, I also have over my shoulder, and I can show you that in a second. But we'll go through how these work. So how these work is, you can see inside, there's kind of a faint copper color and some wires. So what happens is we put a really high voltage across this PMT. So at this end, we have at plus 1500 volts, and this end we have at 0. And what happens when the photon comes in, on this little copper colored bit of glass here, it knocks a single electron loose. But because we have this really high voltage across such a small thing, that's going to accelerate our electron. And it will accelerate it and make it collide with a bit of the PMT. And then it will collide again and again. And it's actually going to look a bit like an avalanche. So as our electron comes in, it'll hit one of these bits and it'll knock a few more electrons off. And then they'll travel to the next stage where they'll knock a few more off. And it will keep going. And eventually our single electron that we started with will turn into 10 million electrons, which still isn't a lot, but it's enough that we can measure them now. Okay, so that's how we get a measurable signal out of these detectors. So one of the things I spend a lot of time doing is testing these PMTs, because it's really important to test them before we use them. So some of the questions I look at and try and answer is, what do our signal events look like in these PMTs? What do photons produce? We also want to know what noise looks like. So noise is basically anything that's not a pulse caused by light. And then finally, we want to know sometimes what affects the noise. So now I'm going to take you for a really quick tour. Like I said, I'm fortunate enough to be in the lab today. So I guess before we go to the tour, I just want to maybe show you a few of the things we have here. So this is a model of what we have in the center of the SABRE experiment. Unfortunately, again, this one doesn't have real PMTs and a real crystal. The crystal would dissolve, and the PMTs are very, very precious. So that we get them they're handmade for us, and they're very breakable because it's glass. So, but this is what it looks like in the center of the experiment. And if you've got questions about it, happy to go through it later. But again, to go through the theory, we have a dark matter particle knock something in our crystal. It makes a small light pulse, which we then detect with 2 PMTs on the end here. So now I'm going to go show you my lab. Unfortunately, I can't show you the one I normally use, which is in the basement here, but because it's being renovated, but I have a temporary one up here, but I just need to throw a mask on. So normally I'm in a really dark lab in the basement here, which is a bit sad, but it's really important for what we do. So this is the lab we're currently working in. It's not very big. Again, it's just a temporary space. But we'll start by going through a little bit of what we actually have here. So if you remember, I said that we try and measure single photons. So that's a really tiny amount of light. We need to make it really dark before we do our work. So how we do that is by using something we imaginatively call a dark box, because physicists are really great at naming things. That's my ongoing comment on that. So what we have here is a big metal box, and inside it, we have another box. And this box here is painted black, and that's to absorb as much light as possible. And in this box, you can see here, sorry, it's not very clear. It's very hard to show a dark thing that's bright. So we have a PMT here. So this is one of the PMTs that we use to measure things. And we also have our setup in here to try and measure single photons. So I'm sorry if this is not coming across very clear. So here for our single photons, we have a laser that gives out a really short pulse. And then this laser passes through a series of stages to try and amplify, to reduce the intensity of our signal. So what is actually in each of these is a little metal disc. And the whole point of that metal disc is it essentially acts basically like a pair of sunglasses, try and show you one that's not mounted without dropping it on the floor. It basically acts just like you'd find with a pair of sunglasses, except it reduces the light by a factor of 1,000 times. It's 1,000 times better than your average pair of sunglasses. So this is where we do all of our actual PMT testing. And then this is what we use to read out our signals and try and get a measurable pulse. So these boards are very, very fast measuring devices. So they read out a sample once every 2 nanoseconds. So that's a tiny, tiny fraction of time, right? So they read out 500 million samples a second. So they're very, very fast, but it's what we need to capture this. So now I'm going to go back to my presentation. Thank you for coming on the very quick lab tour. I'm sorry, we don't have any of our really big detectors here at the moment. They couldn't come upstairs when we moved out of our lab. So I'll very quickly run back across to my other room and then we'll keep going with the talk. So okay. So we've talked about some of the things we use to test the PMTs. Now we can talk about what does our signal actually look like. So on the left here, you can see a pulse from a single photon. So you can see here, it's pretty clear using these detectors that when we have a single photon, the problem is it's over a really short range of time. And even though it looks really big here, it's not. So it's still even though we can do it, it's not very easy. And it's especially not very easy when you're only looking for, as Maddie said, about 1 event per day per kilogram of target. So even though we don't know what dark matter is, we know that if it interacts, based on Maddie's predictions, we'll probably get an event like this. So instead of having just one pulse, you'll have a few pulses. And the orange and blue here represent PMTs in the top and bottom of our crystal. So this is what we think our dark matter events will look like in our crystal, but we need a lot of them to tell it something that's like dark matter. So I guess we've talked a lot about the detector. I want to talk quickly about why do we even go underground for these things? Because it's not an easy place to work. It's a lot of work to have a lab underground. And the answer is something Maddie talked about at the start. We need a lot of shielding for our experiments. So by going deep underground, we can use all of the rock that goes above us to try and reduce that rate of radiation. So Maddie told you we have about 1 million counts per day per kilogram on the surface. So when we go underground, what we get is we get that reduced by nearly 1 in 10 million. So we go from having tens of millions of events per day of external background to hopefully a lot less than 1. And we get that when we go to the depth. So before I talk about the lab that our experiment will be, I have this lovely snow-capped mountain photo. And the reason for this photo is underneath this mountain, which is called the Gran Sasso Mountain in Italy, we actually have another underground lab called the Gran Sasso National Laboratory. And this is, aside from being one of the biggest underground labs for particle physics, it's also the home of the SABRE Experiment's northern twin. So it's this giant space with very large halls. This is just one of the 3 spaces they have underground. So it's a really nice underground lab. And it reduces it by the background by a factor of about 10 to the 7. So only a few particles a day. We, thankfully, we're using a brand new lab called SUPPLE, which stands for the Stawell Underground Physics Laboratory. So as the name suggests, it's in Stawell. So if you don't know, Stawell is a town that's 240 kilometers kind of west, a little bit north of Melbourne. You can see it on the map here. And we're actually going deep underground in a gold mine in Stawell. So our lab will be 1,024 meters below ground in a really exciting space. And this is the photo of what the lab looks like 2 weeks ago. So we've already dug out the space where it'll be. We've put the concrete slab down to the floor, and they're currently painting the walls to try and keep the dust down. So this is a really exciting thing, and it should be finished before the end of the year, which means we can finally start moving our experiment underground and to get started. So finally, the last thing I want to talk about, we've touched on a few things here, is what it's like to actually work in a clean lab. So you saw Maddie talking about having to wear multiple pairs of gloves to handle things. When we work with these really sensitive experiments, it's really important to keep things clean. So it's not just that people can be very radioactive by our standards. You're not actually radioactive to the point of being harmful to you. Just compared to our experiments, we need to do a lot of things to keep things like dust or hair from falling into the experiment. So often when we work in these things, you get these funny photos of us in clown suits with hair nets. We wear gloves. Sometimes we wear multiple pairs of gloves because the pair of gloves you wore when you put on, they've touched your skin. They might have touched something else they weren't supposed to. So you just put another pair on. And we also have to wear multiple pairs of shoe covers and things like that. So it's quite a tough place to work. No matter what the weather is, you're always going to be wearing about 3 layers of clothes, but it's something we need to do to get these really pure detectors. So actually, this is a photo of me holding the powder that we use to grow our crystals from. So before we make them, this powder has a lot of very specific things done to it to try and purify it. And once we've purified it, we don't want to get it dirty again. So we're very careful with how we handle it. So this is the end of my talk, I believe. Yep. So I think now we can open it up to questions, if that's correct.
Yes, that is. Thank you so much, Bill. That was amazing to come into the lab with you. That was just, I don't know about everyone else up there, but I was absolutely glued to the screen and I was about 2 centimeters away to be able to see everything. It was fantastic. Yes, so we've got quite a few questions. We don't have a lot of time, so I'll try and go through a number of them. First of all, a couple directly to you, Bill. First one from Tammy. So how long does it take to make the PMT and how much would it cost? Bit of a money question.
Okay, so I will also show off the other PMT I have at the moment. So these are the quite big ones you saw in the Sabre thing. So something like this, it takes about a month to be made. But unfortunately, one of the few places that actually makes them is in Japan. So even though it takes a month to be made, it takes about another month to get them to us. And because they're handmade, so they are quite expensive. This one here, I think, is about $15,000. This one here is about $18,000.
Wow.
So they're a really quite fragile thing. I'm not sure my boss would like me holding this one so haphazardly. So I'm going to put it back before anyone takes a screenshot.
I was going to say, one of the ways we like to measure the cost of PMTs is in units of PhD scholarships.
Okay.
Yeah.
So if you break it, it's about half of your scholarship for the year.
I haven't dropped one to date, but
let's keep going with that. I think that's good. Yeah. Now the second question, very great one from Max, who I believe was the 10-year-old zooming in. So hello, Max. If the sodium ion crystals dissolve in air, how do you make them? Great question, Max.
That is an excellent question. And the answer is we have to seal them up at every stage. So you might have seen with all the photos that Maddie and I had, we were working in, sorry, that's not the right one. We're actually working in a sealed environment. So right in front of my face, there's a big sheet of Perspex. That's why we have those big rubber gloves. So all of that air in front of us isn't actually air. It's filled with an inert gas, so nitrogen, that's completely dry. So every time we do something with the crystal, it's not actually in contact with air. But it's a lot of work to do this. So it's quite difficult, but that's how. Don't know if you want to add anything on that, Maddie.
No, you've got it right. And that glass bottle thing that Bill's holding in that picture, that's also, we pump it to vacuum or we fill it with nitrogen. Everything takes about 2 to 3 times as long as it normally would because we put in all these extra steps to avoid it being exposed to air.
Amazing. Thank you so much. And thank you from Max in the chat as well. So wonderful. Thank you for the great question. Okay, so a couple of other questions. So Tammy, so I guess this is for both of you. Do we know if dark matter is a tangible form of matter? Over to you, Maddie. Yep.
I feel like that depends on your definition of the word tangible. We can't touch it. We can't taste it, we can't see it. The part of the reason we call it dark is because it doesn't interact with our body or the universe in any way that we do. So it's not tangible in that sense, but it's tangible in the sense that it's real. We know that there has to be something out there because one of the big things that it does is it changes the way that galaxies move. So if you think about, if you've ever like spun a yo-yo around your hand, if it's a really light yo-yo versus a really heavy yo-yo, you have to spin it at different speeds to kind of keep it so that the string is taut. So we can also look at how fast galaxies are moving and work out how much mass has to be at the end in order for them to be spinning that quickly and not falling apart. And that tells us that there has to be something there that's making the galaxies a lot bigger than they actually appear. So it's definitely real and it's definitely doing stuff in that sense, but not in the way that we can touch it.
Amazing explanation, Maddie. That was great. I think for both of you, you've done some amazing work with the analogies of explaining your work, which sometimes is hard to understand. So I think all the audience are very appreciative of that. So thank you. Last couple of questions. So from Sam, Matt, probably to you, Bill. So do underground vibrations in the Stawell mine near the lab affect results? Or do you know if they will affect results?
They absolutely do. So the Stawell gold mine is still an active gold mine. So twice a day, they blow up a bunch of rock. So we have to design our experiment to basically, it has the same technology they use for earthquakes to try and sort of separate it from the ground so it doesn't shake as much. So we haven't finalized what exactly we'll do. It's quite likely that we'll just stop taking data for sort of 10 minutes around that explosion every day, which isn't ideal, but it's better than having data where the detector's not working properly.
Yeah, there's a whole separate set of the experiment that we haven't talked about at all that is basically there to just monitor the conditions of the lab. So things like the humidity, the temperature, how many people are coming and going, how many trucks might be around, when explosions are going on, and things like that. So we can try and decouple all of that information from what we're actually trying to see.
Amazing. All the things you have to work around. Okay. We're drastically running out of time. I've got one quick question and one last sort of question. Well, I'm saying that there's like lots of last ones. Quick one in the lab from Jeff. He said, beards, are they allowed? Over to you, Bill.
They are. There is a very ugly piece of equipment. It's a beard net. Beard net, sorry. Personally, I think it's better to just shave it off and live with that. But there are certainly people who work in these environments with a beard. There's just even less of their face that's visible. You get about a tiny gap in the eyes, and the rest is hairnet, mask, beard net.
So true. Okay, and I guess so overall, this is probably to both of you. So what has been learned about dark matter since people have started studying it, and have there been any important discoveries? So it's a bit of an overview question. Over to you, Maddie, first.
A better way of answering it is probably saying that we've learned a lot about what dark matter isn't. For things like this, it's kind of a process of elimination, a bit of a dance with the people who are theorists and who are designing different kinds of models for dark matter. They say, oh, it could be this. So we go and design an experiment that doesn't see anything. And we're like, well, it's not that, so give us something else. They give us something else. We tell them that that's not it, back and forth, back and forth. So there has been actually quite a big process of elimination to kind of narrow down what dark matter could be. The initial field of view is that it could be anything from the size of an electron all the way up to the size of a black hole. There's this huge mass scale of what dark matter could be, and we're kind of slowly trimming this back, working out what it's not before we can decide what it is.
And I guess I'll just say, we might not have made a lot of progress as particle physicists on what dark matter is, but our colleagues in astrophysics have actually done a lot of really good science understanding it. So we know it's not only something that's in our galaxies, we know it's something that we need for galaxies to have actually formed. They have lots of very, very clever ways of measuring it. And the history of dark matter was a few people going, oh, that galaxy is a bit heavier, to this big journey of it's actually the thing that's sort of not only holding them together at the moment, but it's what caused them to form as well. So it has been a journey of discovery, but unfortunately, it hasn't been particle physics' turn yet.
Oh, I'm sure your turn is coming. And also great shout out to your colleagues in astrophysics as well. Okay, final question for you both. Always the last question. What is next? What's next on the cards? What are we working on next up? Over to you, Maddie, first.
Well, the lab's going to be finished at the end of this year, I think, fingers crossed, given COVID and everything. So what's next is finish up my PhD sometime next year, hop on down to the lab and start getting everything all nice and set up for the real thing, moving away from those simulations.
Yeah, exciting. And Bill, same.
Same
Will
thing, and I
your
guess,
bios continue to go along the same trajectory?
and I guess starting, like, while Saber's being built, it'll take a few years. We're already kind of starting to think about, well, what's the next experiment? What could we do better? So there'll be a lot of really interesting work, trying new technology and seeing how we can use that to make a better experiment with what we've already got.
Amazing. Well, a lot of exciting things to come. Thank you to both of you. That was so fascinating. You just explained everything so well and clearly so passionate about this work that you're doing. So really, really appreciate it. And there's lots of thanks coming in from the chat. So I hope you can read that as well. And thank you all out there as well in Zoom land for coming. Apologies, I went a little bit over. I did the ultimate sin of not finishing on time, but I think you can understand this is really, really fascinating and worth a couple of extra questions. So a few final things from me. So this has been recorded and you'll be able to see all of it online on the Faculty of Science YouTube channel. If you registered for the event, we'll also send out the link when it's up there as well. Also, of course, there's still a couple of days left of Science Festival, so please hop over to the website and find out everything else that is on. And that is including 2 more mid-afternoon masterclasses that are happening tomorrow and Friday. Tomorrow we are all about monitoring, so the weirdest mammal in Australia and what we're now starting to learn about their unusual reproduction. So thank you, Bill, for putting that up. That's what comes. So, oh, that was you, Maddie. Thank you. So thank you, everyone. Hopefully I'll see you all tomorrow. Well, I won't see you, but hopefully you'll be able to tune in tomorrow. So thank you, and Bill and Maddie, really, really thank you. That was so fascinating, and have a great afternoon.
Thanks. Bye.
See ya.
Bye, everyone. Thanks for coming.